Okay, I think we're ready to continue. So, in spite of the results from Deb and Goldberg, in which they indicated that fitness sharing was better than crowding, there was this guy, Mafaud, he was also a PhD student at the University of Illinois. He showed that it was possible to design a crowding scheme that was more powerful than fitness sharing. And he argued only a few minor changes were required for that. So he proposed something called deterministic crowding. So in this case, this algorithm tries to minimize the replacement errors that appear in de Jong's proposal, which was the main drawback. So this was presented at PPSN long time ago in '92. And the main feature of this algorithm is that it introduces a competition between parents and offspring that are located in identical niches. So after performing crossover and mutation, each offspring replaces its nearest parent if it has a better fitness than the parent. So this comes in the PhD thesis of this guy, which is a very interesting thesis because he analyzes many diversity techniques used in evolutionary computation, including microgenetic algorithms and many other ideas. So this is how it works. The algorithm starts by grouping all the elements from the population into n divided by 2 pairs. N is the population size, of course. Then the pairs are recombined, and the resulting offspring are mutated. So for each pair of offspring, 2 sets of tournaments parent offspring are possible. It can be parent 1 versus offspring 1, parent 2 versus offspring 2, and then the other combination, parent 1 with offspring 2, parent 2 with offspring 1. So he performs the tournaments so that the most similar individuals are always forced to compete between themselves and to determine a winner. Because in this scheme, basically, the idea is that if you have individuals that are very similar, this is a loss of diversity. You don't want these very similar individuals to evolve because eventually everybody will be identical. So to prevent this, you force them to compete, and whoever of these 2 similar individuals has a better fitness, you keep. The other one you delete, you remove from the population. So this is an efficient algorithm. The complexity is order n. Then somebody proposed probabilistic crowding. It was mentioned with Goldberg. This was proposed in the Evolutionary Computation Journal several years ago. And the idea is very similar to Mafaud's algorithm, but instead of always deciding in a deterministic way which individual will win the tournament, they use a probabilistic acceptance function. And they showed that this is it's a better algorithm in a sense because it produces more stable subpopulations than when using deterministic crowd. Walter Cedeño and Harik, they propose algorithms that are similar to Mafaud's approach. For example, Cedeño suggested the use of a specialized crossover, this phenotypic crossover, and other specialized operators to reduce the replacement errors produced by deterministic crowding. And this was his PhD thesis from University of California, Davis, long time ago, '95. I haven't seen this guy in a long time. He's from Puerto Rico, but he showed up at some Gecko conferences back in '99, but he is working in industry, so I haven't seen him in a long time. Then there was restricted tournament selection proposed by Harik. This is an approach for multimodal optimization, also a very interesting idea. In this case, 2 elements from the population are selected first, and then they are recombined and mutated. And after recombination, it takes a random sample of CF individuals. This is, again, the crowding factor parameter. And this set is used as in the original crowding algorithm from Kenneth de Jong. So each offspring competes with the nearest individual in the sample, and the winners are inserted into the population. This is repeated several times. So the complexity is CF times n, and it can go from linear to quadratic convergence, to quadratic complexity. This is a very interesting one, clearing, proposed by Petrovsky in '95. In this case, this is similar to fitness sharing, but is based on the notion of limited existing resources in the environment. So instead of sharing the resources among all the individuals, they are only shared among the best individuals in the population. It's kind of an elitist scheme. It's an intriguing idea because normally in fitness sharing, you will share resources with everybody else. Here he says, no, let's go only for the top, for the best. So he preserves the fitness, this is Petrovsky, of the k best individuals, which are, he called them the dominant individuals in the niche, and resets the fitness of the others that belong to the same population. Those are called the dominated individuals. So same as in fitness sharing, individuals belonging to the same niche are penalized if their distance in the search space is less than a certain similarity threshold. This is called sigma s in this case. Is the clearing radius, is not sigma share. And it can be coupled with an elitist strategy to preserve the best elements in a niche. The complexity is Q times N, where Q is the number of niches that are maintained during this search. I have to add, most of these approaches have not been used for multi-objective optimization. Fitness sharing is the only one from the ones I have mentioned so far. And clustering is the second. Clustering, of course, has been used for a long time in evolutionary computation. For example, Jin and Germain in '93 proposed a framework for implementing niches using clustering algorithms. And normally they use k-means because this is like the easiest method for doing clustering, which divides the population into several clusters and considers the centroids of these recently partitioned subpopulations. This is how it works. We have NC individuals in the same niche of individual I. So the fitness is given by this expression. In this case, D max is the maximum distance that is allowed between an individual and the centroid of its niche. Alpha is a parameter given by the user. And DIC is the distance between individual I and its centroid. So you have a circle, and you have the center of the circle, which is the reference in clustering. And you compute fitness of an individual using this very simple expression. Again, as you can see, NC is affecting fitness. So the more individuals you have in the same niche, the more the individual will get penalized. So the fitness will decrease. Thermodynamical, again, they use the principle of minimal energy. This is a concept from simulated annealing. This is the density estimate. So the idea here is that we select individuals such that the free energy is minimized. So the free energy is given by this expression. E, in this case, is the average energy in the system. H is the entropy, and T is the temperature. So it uses an expression from simulated annealing. And diversity is controlled by adjusting the temperature, T, according to a certain cooling schedule, same as we do in simulated annealing. We will talk about simulated annealing later on. So T, according to Kita, T is less sensitive to the population size and to the size of the feasible region than the traditional fitness sharing function. So over the years, there has been a great emphasis on efficiency regarding research on niching. For example, the paper I already mentioned from Jin and Germain, they propose to alternate between clustering and niching to make a more efficient algorithm. And they claim this will reduce complexity from n squared to n times q, where q is the number of niches. But in general, fitness sharing algorithms can work with a complexity n times q. But this can be done only if the fitness values are sampled from a subpopulation of size q. So this is really not a great finding from Jim and Germain. It's just that normally the issue is how many niches we have, because in general we don't know how many we will have unless we preset this value, as it is done in MOGA. I show you the expression from Fonseca. In the case of Fonseca, all he does is he takes maximum and minimum objective function values, he divides that by the population size, and then he says, okay, I need as many niches as individuals I have in the population based on the ranges of the objective function values. There have been also proposals for doing dynamic niching. For example, Miller in 96 proposed to use a fixed number of dynamic niches that had a fixed radii and niche centers, but he used a sorting procedure in the entire population for defining the position of these niche centers. Those individuals not located within any of these niches will undergo a conventional fitness sharing, and they claim this will reduce the computational cost because since we fix already the positions of many of the niches, we are betting that most of the solutions will use one of these fixed positions, and only those that are not using the fixed positions will have to be computed. So this considerably reduces the computational cost. There is also coevolutionary niching. Goldberg proposed this. And this is a very interesting idea. It's inspired on a monopoly competition. So the algorithm has two populations. One contains businessmen and the other one contains customers. So the idea is that we want to set up the populations in such a way that the location of the businessmen corresponds to the locations of the niches and the locations of the customers corresponds to the solutions. So we want to maximize, let's say, the outreach of the businessman so that they can take care of more customers. And we use, this is called coevolution in evolutionary computation. Coevolution is when we have two populations, but the fitness of population 1 depends on some information from population 2, and vice versa. The fitness of population 2 depends on some information from population 1. Coevolution exists in nature, and we will talk about this later on. So in this proposal, the location and the radius of the niches automatically adapt to the specific features of the fitness landscape, or at least that's what they claim. So the algorithm does the thing by itself. Tagging is another interesting idea by William Spears in '94. The idea here is to improve performance of techniques to maintain diversity when they are based on distances. He proposed a labeling system for this. So the idea is that instead of computing distances, he uses labels to identify the population to which a particular individual belongs. So this enforces what we call a mating restriction. Mating restriction means I cannot recombine with anybody. I have to look for somebody who has a label like the one I have, because that individual belongs to the same population. So he argues that this produces fitness sharing as an emerging procedure. This is a very interesting idea. But as I say, none of these ideas have been used in multi-objective optimization. So this simplifies the process of classifying individuals and clearly it reduces also computational cost. So it's a sort of a bio-inspired technique for niche formation, because individuals that belong to a certain species is because their parents were members of that species and not because they lie on a certain position. So unlike fitness sharing, in fitness sharing, you belong to a certain niche because your parents were inside that niche, so you are not going to be generated too far away from your parents. So it's very likely the offspring will lie in the same niche. In this case, it depends on your label. If your parents have a certain label, then you belong to that population, not to the individuals that are close to you. So it's a completely different idea. The multinational evolutionary algorithm proposed by Ursen. This is a very complex model, very interesting. This is a very interesting paper. He considers a world in which there are nations, governments, politicians, all these in his simulations, and there is a dynamics that is dictated by the migration of individuals, the union of subpopulations, and a selection scheme. So he also uses an auxiliary sampling mechanism that is based on the topology, how solutions are connected, and this detects if a feasible solution shares the same attraction point. This is very interesting, and when I read the paper, I got the perception that he was trying to model really a society. This guy is from Denmark. I don't know if it's the Danish society he was trying to model. But the problem it has is not only complicated to implement, but also is inefficient in high dimensionality. Other ideas, the Elitist generational genetic chromodynamics algorithm is a very strange number. In here, they define a mating region. So this is basically like saying there is a neighborhood and we can only recombine with individuals that belong to that neighborhood. So you have a circle and there are many individuals. Perhaps there is another circle here, other individuals. But for example, this guy, A, cannot recombine with B because they are not in the same neighborhood. They are not in the same circle. So this imposes geographical restrictions to recombination, which is a very interesting idea. So, okay, this one is also considered a variation of fitness sharing because it still uses a radius, and you can do weird things like put some sort of overlap, like part of this circle could be above this other circle. You can do strange things like that. Senergy is an indicator that was proposed some years ago. Most people are not aware of this paper because of the place where it was published in the notices of the American Mathematical Society. It's a very interesting indicator, and my students have been using this recently for assessing uniform distribution of solutions. Somebody was asking me in the break, in multi-objective optimization, normally we have to measure two things. One is convergence, and the other is how uniform are solutions in the Pareto front. So sometimes an algorithm is very good in convergence, not very good in distribution of solutions. However, convergence is more important than distribution. If you always win in convergence, that is good news. But if your distribution is very bad, that is bad. Nobody's going to like your algorithm. If you have a decent distribution, not the best, but very good convergence, that is good. Of course, if you have good convergence and excellent distribution, you are awesome. Your algorithm is really wonderful and everybody will want to use that algorithm. It's normally difficult to achieve the two things. However, the indicators that we have normally used to assess uniform distribution are designed for low dimensionality. For example, we use something called spacing, and we will talk about this. Spacing measures that solutions are equidistant, one with each other. Like this solution with the next one is at the same distance as this solution with the following one, and so on. So this doesn't make sense if you have 10 objectives. How are you going to measure that? This indicator, however, can work with any number of objectives. It's related to entropy and basically tries to measure the anti-entropy of the system by using the energy, or that's what they call it, the S-energy, the energy in the system. It's not completely straightforward to implement, but it's not that difficult. And it's an interesting idea. Other ideas, for example, the moment of inertia. Morrison, who was a PhD student of Ken de Jong, he proposed a measure of population diversity, which is an extension of the inertia for measurement of mass distribution, but this goes to high dimensionality spaces. So it's an expression like this. In here, we have these coordinates of the centroid, is C, and X are the solutions, of course, and P is the population size. So what he does is he computes this I, and this I is the moment of inertia in the population, and this value will give us a measure of diversity that he argues that is a more accurate measure and it's not that expensive to compute. It's quadratic on population, it's 4 times n times p, where n is, I believe, what is n here? I think it was here. Yeah, it's the number of decision variables. And p is the population size. And he argues that any method that is based on pairwise comparisons requires p squared complexity. So his complexity is lower. However, this is sort of an obscure paper. Most people are not aware of this technique. Then we have ectropy. This is not a typo. It's not entropy, it's ectropy. It was proposed by these guys, Lasevic and Almadi. And this is the sum, is based on the sum or the average of pairwise distances between points in Rm. Well, no, they say these distances based on pairwise distances, this is the same as Morrison. They have several shortcomings. For example, they will reach their maximum value when the population has very few mutually distant clusters of collocated points. So they propose this notion they call ectropy, which is the opposite from entropy. And they say this is a measure of disorder in the population. Rather than a measure of order, which is entropy, this is a measure of disorder. And the aim is reaching a near maximum value for the population that has many collocated points. They basically criticize methods based on clustering. Clustering uses this idea of pairwise distances between points because they measure with respect to the centroid. And they say this works a lot better. Another technique that has been used for maintaining diversity is what we call mating restrictions. This is a very old idea. If you read Goldberg's book, he mentions that it has been used for many years in the literature for minimizing, for example, the appearance of what he calls lethals. Lethals are offspring with a low fitness value. They, in America, we made many jokes about this because when I was living in the US they have this association called Mensa. And it's an association only for people with a high IQ. So to enter Mensa, you need to have an IQ of at least 130. Otherwise, they won't take you. So I knew people, some faculty at my university, who were obsessed. One of them was my advisor. They were obsessed with this thing. So he wanted to meet a woman who was a member of Mensa. Because the underlying assumption is, if I'm very smart and I marry a woman, doesn't matter how bad looking she is, but she's very smart, my offspring will be smart. This is not always true, right? You should not mess with nature, because nature sometimes plays really bad jokes to you. So these guys, what if the offspring are not smart? They will be called lethals. You know? The parents were okay. Genetically, there was nothing wrong. Actually, they were actually very good. But something happened. You know, nature played me a joke here. And my son is very dumb. You know, he's really stupid, so he's a lethal. So lethals, you want to eliminate. In evolution, of course, you cannot kill your son. Well, you can, but you should not, because it's very bad to do it and you will end up in jail. But in the simulation, we can do anything, right? So we don't like our children, get rid of them. You know, just kill them if they are lethals. So this has been done for a long time in evolutionary computation. It's not a very common mechanism. A few people have tried this over the years. Mating restriction means that I will impose rules on who can recombine with whom. It's not completely random as it normally happens in an evolutionary algorithm. You know, in life it's not entirely random, right? There are some criteria. Some people are more demanding than others, but at the end of the day, we normally have some criterion, or at least most people do. But in the simulation, again, we can do anything. Somebody proposed a technique called selection by seduction. You know, you're probably not very good looking, but you are very good when you talk. Right? You can seduce the others, and that's valid. So you can do anything you want. In the simulation, we have even more flexibility. For example, Goldberg analyzed an example of mating restrictions based on genotypic similarities. this means I will only mate somebody who is genetically similar to me. You know, the other person has a binary string, and I do have a binary string, so we measure Hamming distance. If it's below a certain value, that means we are very similar, so we will mate. This is a mating restriction. Biologically, mating restrictions are equivalent to geographical isolation because we are setting up a barrier to restrict the flow of genes. And this allows to complete what we call speciation. I mentioned yesterday that mutation does not produce a new species. Isolation is what produces a new species. So if you have in your simulation mating restrictions, this not only encourages diversity, but encourages the generation of new species. So this is very interesting. So geographical isolation is a key component of evolution because it creates basic conditions for speciation. So for the new species to appear. So that's the reason why it should not be surprising that several niching techniques rely on mating restriction. And this occurs in nature. So Goldberg and Deb, in his paper on fitness sharing, they suggested the use of mating restriction based on phenotypic distances. The idea is to allow two individuals to recombine only if they are very similar. However, there were some people who contended this, who say this is not right. But the idea is to produce different species in the population. And Melanie Mitchell is the girl in the picture. She analyzed this. When we implement parallel genetic algorithms with the island model, in the island model we have several islands, which are the processors in which we are running our genetic algorithm. We also use mating restrictions because normally you can only recombine with individuals that are in the same island. You know, it's like you live in a city, so normally you are mating with somebody from the same city. It would be very uncomfortable to have to fly to Europe to mate and then come back, right? I mean, I know some guys who are actually able to do that, but normally most people won't do that, right? You try to mate, perhaps because it's more comfortable, because this is the place where you live, because you like this place. There are a number of reasons for humans, but there are also practical reasons for doing that. So in a simulation, we don't allow an individual in one island to migrate to another island to recombine and then get back. They only can recombine with other individuals in the same island. So this is a geographical restriction. It may be also in the old days, when we had these computers with many, many processors. This is not common anymore. But and the old days is like my time, you know, like 25 years ago. We had these architectures with thousands of processors. There were these computers in which they had, for example, something like this, a mesh or a grid, and the intersections contain processors. All these were processors. So you probably had, I don't know, 12,000, 20,000 of these processors. And you wanted to run a genetic algorithm here. So in this case, what people use was a neighborhood structure. They will say, okay, all this part is a neighborhood. So this guy here, A, can only recombine with other individuals in the same neighborhood, cannot go beyond the neighborhood. So we had to establish rules like that based on the topology that we use to interconnect individuals. But this is not very common today because these multiprocessor computers are not very common anymore. We now use clusters of computers or the cloud and all these things, grid computing. Now, some researchers have indicated that mating restrictions should motivate the recombination of different individuals rather than similar individuals. The first person to make this claim was Larry Eshelman. Larry Eshelman, back in the 80s, he wrote a paper in which he said we should not recombine individuals that are very similar because these individuals are relatives because their code is very similar. So you are having incest because you are recombining with a relative. So you should not do that. You should go for individuals that are different, maximize the difference. And this prevents the generation of lethals. So this is a debate. It's not very clear which one should be used, but it's not common. Very few multi-objective evolutionary algorithms incorporate mating restrictions. For example, Moga from Carlos Fonseca incorporated mating restrictions. Flavio Baita, also Dan Loveling, they had solutions in a grid and restricted the area within which individuals could recombine. Liz and Ivan, we already saw this one, allowed recombination of individuals that had a different gender. Only those of different gender could recombine. Jacob, this is a paper from PPSN, implemented a mating restriction mechanism based on the values of the weights of each solution. So a few people have done this, but it's not very common. Also, when we use mating restriction, there is a parameter called sigma mate. And it's not very clear what should be the value. This is the threshold, how different or how similar they should be to recombine. And since evolution and multi-objective optimization people are very pragmatic, they say, oh, sigma, let's put the same value as sigma share. They have no relationship with each other. But what the hell, I don't know what value to give it, I'm going to give it sigma share. This is, of course, wrong because it's a completely different thing. One is for establishing the niche radius, and the other one is to establish how different solutions should be. But it's unclear what is the effect of this parameter on the performance of mating restrictions. And in most cases, when they use mating restrictions, it's not very clear why is that they are required. And there is actually no evidence that this is of any use. Still, people have used this, but there are few studies that provide empirical evidence of the usefulness of this mechanism. For example, Sitzler showed that for different values of sigma mate, no actual improvement in performance was detected. So apparently had no positive or negative effect. It just had no effect at all. Shaw and Fleming reported similar results in another paper. And Horn offers some empirical evidence that contradicts the foundational principles for using mating restrictions. So some people have said that it's pointless to use mating restrictions. Horn indicated that recombining solutions whose associated vectors are in different portions of the Pareto-Fromm approximation that we have at generation t can indeed produce offspring whose vectors are in the Pareto-Fromm in generation t plus 1. However, these offspring will be located between their parents. So his argument is actually quite interesting. He says it doesn't make any sense to restrict the mating because the crossover operator will always generate solutions that lie between the parents. Recombination is some sort of interpolation operator. So no matter how you restrict this, the solutions that you produce are really conditioned by the nature of the crossover operator, not by the nature of the restriction. So all you are doing is to produce solutions that apparently will be better, but they are always constrained to lie between the parents. So no matter what you do, that's what you will produce. So his argument is actually quite interesting, but not many people took this very seriously. Mm-hmm.
So you have been telling us about the different versions or variations of this multi-objective algorithm. If I want to apply something on a say use case or a practical application, so what is the kind of argument or idea behind to choose which version to use? Does it depend on the basic idea of this algorithm? Is there a relation between the idea of whether it's geographical based or economics based and the practical application, or it doesn't work that way?
No, it doesn't work that way. Actually, Well, most people, when they don't know what to use, they use NSGA2, just because the code is available. But this is the $1 million question. They always ask me that. How can I select that? And I do have a short answer for that. You don't know how to select one. Because we, in general, we don't know what specific features we need for a particular problem. I can tell you, for example, if the problem is the decision variables are real numbers, then something like NSGA2 should work, or MOIA-D. Those are good algorithms. If you are using binary numbers, any of these two algorithms works fine. But if you have a problem in which the decision variables are permutations of integers, for example, then there is something else you should use. You can still use these algorithms, but the performance is not that good. We will get to see taboo search. Taboo search is much better in that domain. So it really depends on the problem. But we don't have a magical recipe, a taxonomy that says if it's flow shop scheduling, you have to use this algorithm. If it's structural optimization, you have to use this. It's really based on experience. And even people who have been working for many years in this area, like in my case, we don't know for sure. When they try something and they show me results of what is wrong, then I can get an intuition on what could be wrong. But it's only an intuition. I may be wrong. I may be completely wrong. So far, I haven't found a problem in which we haven't been able to apply some of the algorithms we have. Of course, that problem certainly exists. We haven't found it yet, but it must be there. But I have to tell you, some of these problems are very difficult. I will probably tell you at the end, in the last part, when we see applications, I had to solve some problems some years ago that was a headache for me. It was this problem from NASA. They wanted to optimize the change of orbit of a satellite that they sent to take pictures of a moon of Jupiter. And this problem, the main difficulty, they had already used a genetic algorithm, a multi-objective genetic algorithm, but the problem was that the number of decision variables was not fixed. It was variable. So it could go from 30 to thousands of decision variables. So we had to bound this to 13,000 decision variables. So the problem in this case was the very high dimensionality of the problem. If you ever try to solve a problem with more than 1,000 decision variables, everything that could go wrong will go wrong. It's very, very hard. Not because of the problem. It's because of the storage, the operators, they don't have any effect. You can imagine if you have a very long string and you apply crossover on 1 point or 2 points, it has no effect. So you are almost randomly moving in this huge search space. So how do you find a solution in there? Today we already have algorithms for that, for high dimensionality. But at that time, in 2004, we didn't have any. So we suffer a lot. We had to use some sort of brute force approaches to do this. And also, the objective functions were very expensive because they had to solve a system of differential equations, and they were using Runge-Kutta order 4. So at that time, it took 8 minutes a single evaluation of an objective. So one simulation, the full simulation took 2 weeks, a single run of the algorithm. And sometimes after 1 week, you realize there was something wrong, and the thing crashed. So it was very bad. The student who did that almost committed suicide. But at the end, he managed to solve it. Mm-hmm.
So say for a particular problem, I have implemented 4 or 5 optimization algorithms, say PSO, GSA, anti-colony optimization, Nakaku search. And certainly I have got better results for PSO. Mm-hmm. And I'm writing a paper using that results. And then some reviewer comments like this, that how did you decide it? Like, why did you use the PSO? Then how to defend these like such comments?
Well, I was not the reviewer, right? So, yeah, well, it's difficult to defend this, but this we will find all the time. If you use several algorithms, it's very easy to defend this. You can say, I tried all these algorithms, and PSO gave me the best results. The truth is most people don't do that. They use the algorithm they find, some obscure algorithm, then try, it works, and they try to publish that. So of course a reviewer will ask you, why didn't you try NSGA2 or MoIAD first? You know, that's what any multi-objective guy will do.
Should I show the results of other algorithms too?
Sure, of more standard, at least MoIAD, for example, and show that you are better than that, then nobody will ask you any questions.
And sir, one more question. Say we have some objective function, for say we have problem, vehicle routing problem. In that case, we need to solve a TSP, traveling salesperson problem. Then the objective function itself is a NP complete problem. So is it good to solve these kind of problems using methods?
Sure, they are designed for those problems. It's just TSP is now a very competitive area. You know, in my time, anybody who could solve more than 100 cities, it was a great achievement. Today, less than 1,000 cities is no fun.
So should I use some
Then how you decide that which algorithm is working good? Because you don't know the solution. If you are applying lots of algorithm in that problem, then how do you decide which algorithm is giving a better result?
Well, we always use a standard algorithm first. If that works, that's it. If it doesn't work, then you have to, you got my attention. Right? If you give me an arbitrary problem, what I will do is to try either NSGA2, MoIAD, SMS-IMOA, one of the algorithms we have designed. If that works, I will send you the results and I say goodbye. Good luck with your problem. But if it doesn't work, then you got my attention. I will tell you, okay, I want to know more about this problem. 95% of the time it will work. Well, I found a solution, gave it to you, you are happy. That means it worked.
You said that for any problem, these algorithms are going to give a solution.
They produce a solution. That doesn't mean you will be happy with this solution. That's different, right? They always produce a solution. There are stochastic algorithms. But sometimes the solution is very bad. Sometimes the solution they produce, you look at the solution and say, this is garbage. This is of no use to me. And you will give me the reasons why this is of no use. Sometimes the algorithm crashes. This is very rare. But it may happen. The algorithm crashes, is unable to produce. Imagine a problem with many constraints. A highly constrained search space. So you give me the problem, I try my algorithm, and it's unable to produce any feasible solutions. Then you got my attention. Because this seems to be an interesting problem.
That implies that if I am solving any problem, first I should have an idea of the solution.
No, not necessarily. No, that's not required.
You said
No, but you will know if the solution is acceptable or not. That's what I expect from you. Not that you know where is the optimum, right? That you are not supposed to know. But you can tell me if this is an acceptable solution or not. Sometimes the solution is very bad. Perhaps you already use a mathematical programming technique and you got a better solution than mine. Then you are not happy with my solution. And you will tell me. So all kinds of strange things. You know, I have been more than 20 years in this area. I could tell you some really weird problems that people have not given to me, but they talk to me about these problems. They are really strange. For example, problems in which there are constraints that appear at some moment in the search, but then they go away. So these constraints are active only in a certain moment in time. And after something happens, they go away. So how do you solve a problem like that? So there are all kinds of strange problems. And this is a real world problem, the one I'm telling you about. These problems in which the objective function is very expensive and you cannot afford performing too many evaluations. Problems in which you don't have the objective function. We solved once a problem, a mechatronics problem, in which all the guy had was the gradient of the objectives, but not the objectives, only the gradient. So we had to use MATLAB to estimate the objective function values, but this problem was dynamic. He was modeling the gear in a car. And it was dynamic in the sense that we had to run a simulations for different times. For each time lapse, we got a different solution, and then the objective function was the cumulative value of all these intervals. So it was extremely expensive to perform a single evaluation. And this guy, he designed a multi-objective evolutionary algorithm based on differential evolution that worked okay. I mean, he was happy. And he built the actual thing, the device he was able to construct based on the simulation. So that's what I'm saying. The expert is the guy who gives me the problem. If you cannot tell me if the solution is good, then don't give me the problem. I'm not expecting you to know the optimum. I'm expecting you to know if this is good or bad. Because sometimes the solution that the algorithm produces, it looks very good, but makes no sense in reality. I can tell you some stories about that as well. All kinds of things happen. When I was in England many years ago, after I got my PhD, I was working there for a few months. And I met a guy from Yugoslavia. He had been at the Max Planck Institute. And when he was at Max Planck Institute, they were using evolutionary algorithms in all kinds of industrial applications. So one day a guy came and told them he had this interesting optimization problem that they had already solved using mathematical programming technique. And what they wanted to know was if the evolutionary algorithm could do better. So let's say I have a piece of land, it's a polygonal shape, and inside this piece of land I want to put a cemetery. I want to bury people there. So you have the rectangles are all the spaces for burying people. This is a cemetery. This is not like building houses, right? These guys are not very demanding. They don't need a park. They don't need a lot of light. And these are passive customers. They won't complain. So they wanted to know what was the maximum number of people they could bury here based on this polygonal shape. So it's sort of a standard civil engineering problem. And since they already had a result, was the outcome of a mathematical programming technique, if you work in optimization, you will know that when they give you that result, you aim to improve this, but not too much. If you improve too much, something went wrong. Don't open the champagne first. They just try to analyze what happened. So this is exactly what happened in this case. They modeled this with an evolution strategy, ran the evolutionary algorithm, and the algorithm gave a result that was about 30–40% better than the result these guys had. And instead of celebrating, they said something must be wrong. This solution cannot be right. So, computer scientists, if something goes wrong, you turn off the computer, turn it back on. And that's what computer scientists do, right? And let's run the algorithm again, put the parameters, run it again, get the same result. Say, damn it, I'm sure there is something wrong. I don't know what is wrong. So second thing a computer scientist does, if turning the computer off and back on doesn't work, second thing they do is to plot the solution. Computer scientists are very visual. When they plotted the solution, then they found out what was wrong. They forgot to put a constraint in the model regarding how people were going to be buried. So the genetic algorithm suggested to bury them like this. If people are standing up and not, like this, you can increase like 40% the number of people you can bury. Of course, there will be some complaints if you do this. So they realize for humans it's an obvious constraint, not for the evolutionary algorithm. This is not an obvious constraint. If you are asking the algorithm to maximize, well, that is the optimum. So that's what I'm saying. Sometimes the solution looks very good, but it's not acceptable by humans. Humans will say, no, this is not what I want. So that's why we always need the human expert, because sometimes the solution is deceiving. We believe it's awesome, and we are celebrating, with the champagne and publicizing the thing, and they come and say, this is garbage. What you did is absolutely stupid, and you don't know what you are doing. Because we didn't know. In this case, it's very obvious, but in some cases, we don't know if this makes any sense at all in the real world. So we always need the expert. But most problems I have seen, and in Mexico there was a time in which people would bring me problems all the time, we can solve with very simple algorithms. I can tell you this is not very exciting for me as a researcher. I have been designing algorithms for more than 20 years, but that doesn't mean I'm not willing to help people, right? These guys were so happy because they could solve this complicated problem. For them, it was complicated, not for us. Our algorithms were way above the complexity of these problems. But this I can understand, and it's okay. There is no problem. We can do it, but we will do it once, give them the result, and say goodbye. I don't want to see you anymore. Go ahead, and that's it. Because this problem is of no interest to us. However, when the problem, like the NASA problem, when it's very challenging, then we put a lot of effort in trying to figure it out. Because many things will come out of this, even if we don't manage to solve the problem, which was the case. In this case, it took us so long that by the time we solved the thing, the satellite was gone. So the result was of no use. But yeah, this is very tricky to know which algorithm to use. We will talk a little bit more in one of the practical sessions about that, how to select an algorithm. But in general, the answer is that 95% of the time, any out-of-the-box algorithms will work. And my advice is, don't try to implement these algorithms. The source code is already available. Even if you are really bad programmers, the probability of screwing up this code is very low. Well, it's possible. I have students who have done this, but it takes an effort to do it. And normally the errors they make is on the parameters, not on the implementation, because the implementation is already there. So you minimize the risk of doing something wrong with the algorithm. That doesn't mean it will immediately solve the problem, because you can do something wrong when introducing the information of the problem. Many things can go wrong, but at least you know the code is reliable, because many people have used this code. So you should start with that. If that doesn't work, then you have to start thinking what to do next. The problem today is many people, they publish by using very unusual algorithms. There are all kinds of strange algorithms. I mentioned that yesterday. And it's okay, there is room for everybody. But then they will ask questions. Even PSO is not that rare. It's a very popular algorithm. But they will ask you questions like, why do you use PSO? Why don't you use differential evolution, for example? Why don't you use a genetic algorithm? And this is reasonable, unless you can show that you have used these other algorithms, and you just found that this is better in this particular problem. We have a famous theorem. It's called the no-free lunch theorem, that says that no metaheuristic can be better than all the others in all classes of problems. This is impossible. It was mathematically proved back in '92. So this cannot exist. What we can have is some metaheuristic that for some particular domain is very good. For one class of problems is very good, better than the others, but only in that class. You go to another class, somebody else will be able to outperform. Some years ago, I had a student who was really, really dumb. I had a lot of difficulties to graduate this guy. Not smart at all, very nice guy, but nothing in here, empty head. And we struggled a lot with his master's thesis. And at some point, instead of getting angry, I was excited, because he designed an algorithm that was so bad that it was outperformed by everybody. So at some point I got excited, because the no-free lunch works in the two directions. This algorithm is not supposed to exist. It has to be good in one domain. The thing is to find the domain, because every domain we tried, the thing lost. And at some point I was excited. I said, well, we're going to defeat the no-free lunch theorem here. We're going to show these guys they are wrong. Because this algorithm is such a piece of garbage that it loses. Any domain you try, it loses. But, I was not lucky enough. We finally found a domain in which it worked. But, yeah, it can work in the two directions. Sometimes you design excellent algorithms. Sometimes you design really bad algorithms. It depends on the designer and the creativity of the designer. Some designers are not very good. Okay. So basically, this is just the detail of the algorithm of Jeffrey Horn, the argument of Jeffrey Horn regarding not using mating restrictions, what he says is it doesn't make any sense because if you recombine the similar parents, the solutions are still lying in the same area, so they will produce solutions that are already in the Pareto set, which is P, or the Pareto front, which is PF. So we can conclude that it's unclear if there is any real benefit of using mating restrictions. Of course, we will expect this mechanism to be useful in a certain situation, it's just we don't know exactly when to use them. It's not very common to use this mechanism today. Most of the modern multi-objective evolutionary algorithms don't adopt mating restrictions at all, but they are there. There are many other techniques to maintain diversity. As I mentioned, the PhD thesis of Mafaud is a good reference, but only a very small percentage of them have been used in evolutionary multi-objective optimization. There is also no evidence regarding the advantages or disadvantages of using some particular technique to maintain diversity, at least not in the context of multi-objective optimization. So for example, we know that techniques such as fitness sharing can be used with any number of objectives, which is not the case, for example, of the crowded comparison operator of NSGA2 or the adaptive grid of the Pareto archive. That we know, but we don't know much more than that. It's unclear in which space should we apply fitness sharing. Should be in decision variable space, on objective function space. In operations research, normally they do this, they care more about decision variable space. In evolutionary multi-objective optimization, we care more about objective function space. So it's really up to us, right, where we want to do it. There are many other references on this topic, some good book chapters and papers if you want to know more about this. Okay, the next topic is secondary populations. This is related also to diversity. Secondary populations are also called external archives, and I already mentioned they are necessary to guarantee convergence. This was proved by Gunther Rudolph back in the year 2000. And this is the correct paper. I put the wrong paper in the morning. So there are some issues when we use a secondary population. Secondary population is a data structure. It's not an archive. It's called archive, but it resides in main memory. So should the secondary population participate in the selection process? For example, as we do in the strength Pareto evolutionary algorithm from Sitzler. Most of the algorithms we have today, they don't allow the secondary population to participate in the selection process. What sort of filtering scheme should we use to bound the size of the secondary population? So if the size grows too much, obviously the selection pressure will quickly dilute, which is the reason why Sitzler used clustering. Can we use the secondary population not only to store non-dominant solutions, but also as a density estimator? The answer is normally yes, and many people have done this. So the reason why we need a secondary population is because a multi-objective evolutionary algorithm is trying to construct a discrete image of a Pareto front that is probably continuous. We are approximating in a discrete manner something that is continuous. So it's recommended to keep as many non-dominant solutions as possible, at least at the beginning of the search. Then we can discard some of these solutions, because this will encourage a good distribution of solutions. So the early multi-objective evolutionary algorithms use secondary populations that were implemented as linear lists, very simple data structure, to store non-dominant solutions. But over the years, several more sophisticated data structures have been proposed. For example, Sanaz Mostagin, she proposed to use quad trees in the strength Pareto evolutionary algorithm. And this work is based on an early paper from Havenich from 1983, who used quad trees to identify non-dominant solutions. Other people also use similar data structures like Son and Ralph Stower. Mostagin compared arrays with three types of quad trees, the one from Havenich, the version that she produced, and the one from Son and Stower. And she showed that the use of quad trees is beneficial, but only for very large archives, when you have at least 5,000 solutions. Because if the archive is smaller, then an array is very efficient, because the array is direct access in memory. Something interesting is that she reported that quad tree 1, which is not her algorithm, is the best algorithm from the tree for archives with 5,000 or more solutions. But what is remarkable about this is that these two other proposals, her algorithm and Son and Stewart's algorithm, are supposed to be improvements on Havenich algorithm. But in the study, it shows that's not the case. This algorithm is still better. Jonathan Filsen in 2003, he published an interesting study in which he analyzed the bounding of the size of the external population, and he argued that this produces a shrinkage and an oscillation phenomena in the Pareto-Front approximations. So he says that it would be better to use unbounded archives. And this was, of course, some sort of a strange idea at that time, back in 2003. He proposed the use of two data structures, the so-called non-dominated trees and the PQRS trees, for storing and retrieving solutions from an unbounded archives. Because the main problem with an unbounded archive is you may have thousands of solutions inside. So if I want to get a single solution, I want to do it very efficiently. So how can I do that? And there are data structures. This is Jonathan. He also proposed the use of a secondary population for defining a stopping criterion for a multi-objective evolutionary algorithm. This is the paper from 2003. This is a topic I wanted to touch. Marco Laumans, he proposed a relaxed form of Pareto dominance called epsilon dominance. And this was used as an archiving technique that allows to filter out solutions generated by a multi-objective evolutionary algorithm. This is a very interesting idea. So let me see. Yeah, I have it here. This box in here will be the feasible region but for a multi-objective problem. And this point here is the bound in the low corner that I will obtain with normal dominance. So this point dominates all this region. Okay? This is normal Pareto dominance. In epsilon dominance, we relax the original definition of Pareto optimality. So in this case, we extend the area using a parameter epsilon. That's the reason why this is called epsilon dominance. So you see the point was translated to this position. So now this point represents the dominance in the box with respect to the whole box. So how is this used? This way. If you remember the adapted grid from Joshua Knowles, it's a similar idea. I have objective 1, objective 2, but in this case, I have epsilon values. So I have epsilon here, epsilon here. These two epsilons are not necessarily equal. These can have one value different from this value. We compute epsilon in each dimension. And this can be used in any number of dimensions. So we build the boxes. All the boxes are rectangles of size epsilon. This will be epsilon for F1, epsilon for F2. Okay? So I will be storing my non-dominant solutions. Well, all the solutions I store in this archive. These solutions with a clear color are solutions that I will use to compare. Well, I won't go through the example that is explained here, but the rule in epsilon dominance is in each box you can only have one solution, no more than one. So in this case, for example, I have two. If one solution, for example, 1 in this case, dominates solution 2, then I keep solution 1, get rid of solution 2. That was easy. But what happens, for example, in this case, 3 and 4 are both non-dominated. Okay? So in theory, I should keep both, but I can only keep one. So what I do is I measure the distance between each solution and the lower left-hand corner of the box. So whoever has the shortest distance, I will keep. So in this case, it's 3. 3 is closer from this corner than 4. So I have to figure out rules so that always in each box, I keep one solution. Okay? So far, so good. Seems very easy, right? So what do I gain with epsilon dominance? 2 things. Epsilon can be used to regulate convergence. So if I define a very large epsilon value, since I only have one solution in each box, my algorithm will converge very quickly, but it will produce very few solutions. If epsilon is very small, it will take longer to converge, but the Pareto form will look very nice, many solutions. In this paper from 2002, Marco Laumans and his co-authors claim that they could guarantee convergence using epsilon dominance. Mathematically guarantee convergence. So everybody got really excited. We finally have a mechanism with which we can guarantee convergence. Not based on properties of the main population, but based on properties from the archive. Everybody was happy, celebrating, and in 2004, we found out that the proof was wrong. You know, so sad. So Marco and Oliver Schutze, my colleague, and myself got involved in fixing this thing, but we believe in general cannot be fixed. It could be fixed only for some particular cases, but in general cannot be, we cannot guarantee convergence based on this notion. So epsilon dominance has some limitations. For example, we can lose many non-dominant solutions if the geometrical shape of the true Pareto front is unknown. For example, when it's a straight line, we will lose practically most of the straight line, or almost all of it. The extreme portions of the Pareto front will always get lost for obvious reasons, because they will go above another point, and if we measure distances, this other point will win. So we will always lose the extremes. Segments that are almost horizontal or almost vertical will also be lost. And the upper bound on the number of points allowed in the external archive may be very difficult to reach. So if we use a non-adaptive scheme, that means the epsilon value is kept at a fixed value, then this upper bound can only be reached when the true Pareto front is linear. So it has some disadvantages. There have been some proposals, for example, with Alfredo, is a guy from Spain. We collaborate with him. This guy is an interesting guy. He's a pure mathematician. His PhD was in algebra. But he wanted to get into multi-objective because he could not get a job, right, as a pure mathematician. So he said, I want to do something more practical. So he moved to multi-objective optimization. We were working with him for several years. So he proposed a very interesting approach. He tries to guess the shape of the Pareto front using this family of curves and doing some pre-sampling of the population. So through this pre-sampling, he can guess the shape, and based on the shape, he uses boxes of different sizes. Not all of them are of the same size. And by doing this, we can improve a lot the performance of epsilon dominance as an archiving technique. So this was a very interesting approach. There was another proposal in which he added an extra objective to retain solutions that were normally lost. So this is even better, but this other proposal most people didn't read. They didn't pay attention. The other one was relatively popular. Still some people use this today. Oliver, he has been working with us for about 10 years at Simvestab. He's a German guy, but he married a Mexican, so he ended up in Mexico eventually. He developed some archiving strategies for stochastic multi-objective optimizers. We collaborated for several years, but eventually he went back to his area. He works more on numerical methods, not evolutionary algorithms. And his PhD thesis was in these techniques called set-oriented methods. these set-oriented methods are very interesting. They have been used a lot for multi-objective optimization. And the idea is you have a volume So the idea is you have a volume, and inside this volume, you have the Pareto front. They start from the assumption that the Pareto front is a manifold, which is a reasonable assumption, and they start coding parts of this using some numerical methods. It's like they have this big piece of marble, they start sculpting the marble, removing parts, and eventually they produce the Pareto front, which is probably a surface, right? It's probably something like this. They start coding this with these numerical methods, and eventually they produce this. But the advantage of these methods is you can guarantee things. You can prove things about them. So he started with this. He also developed some archiving techniques for reducing the number of solutions. When you had thousands of solutions in the archive and you wanted to keep only a representative sample, he developed techniques to do that. However, the paper I'm mentioning here is the one in which we fix the part of the original proof of convergence provided in the epsilon dominance paper. This was presented at Gecko in the year 2006 and got published in Evolutionary Computation in the year 2010. Basically, it's two archiving techniques, and we were able to prove convergence with probability 1 to gut-free Pareto front approximations under certain sort of mild conditions, we could say. It's not as general as the original proof of epsilon dominance, but I will say is good enough. Of course, most people didn't like the paper because they were already disappointed with the epsilon dominant thing. And at this point in 2010, most people were not using epsilon dominance anymore. Today, a few people are bringing this back because epsilon dominance can be used in many objective optimization. So some people are sort of looking into that again. Knowles and Korn, they wrote a very interesting paper in 2003 in which they analyzed 3 convergent archiving algorithms: unbounded, simple bounded, and the S-metric archiving. The S-metric is based on the hypervolume. S-metric is another name for the hypervolume. So the 3 are able to converge to the true Pareto front under certain conditions. But in general, they cannot maintain a well-distributed set of points along the Pareto front. So they proposed their own technique called the adaptive grid archiving, which is a variation of the one used in the Pareto archive evolution strategy. They show this has a low computational cost, that is able to adapt itself to the values of points in objective space, and is able to maintain a non-dominated set archive, which uses something they call crowding, but this is not the same crowding as NSGA2. This is a mechanism that encourages an even distribution of points. So for this algorithm, they show that although convergence to a subset of the true Pareto front is not guaranteed, they cannot guarantee this, under certain conditions, at least the boundaries of the grid are able to converge. And when this happens, certain grid regions will become constantly occupied, which guarantees a certain minimum quality of points in the archive. So this is sort of good, not as good as one would expect, but it's reasonable. They also discuss under what conditions this will happen. Brinkman proposed another archiving technique, the approximation guided evolutionary algorithm, AGE, which uses an unbounded archive. He stores all non-dominant solutions generated and uses the external archive to assess the quality of the population. And he does this by computing an additive approximation to the true Pareto front with lexicographic minimization. It's a very theoretical paper, but quite interesting, very interesting work. There is another paper in which they propose the adaptive objective space partition in 3. And this is used to divide objective space into appropriate partitions. It's a tree structure that stores partitions in the leaf nodes, and the partition size, shape, and location in the objective space is determined by the traversal path from the root to the leaf. So you can do very interesting things with this data structure. And basically, they do the theoretical analysis of this structure. And it's another mechanism to preserve non-dominant solutions in a more efficient way. And it has advantages with respect to the adaptive grid. With Saul is a former PhD student of mine. He explored the convex hull of individual minima for maintaining well-distributed solutions in the secondary population of multi-objective evolutionary. A very, very interesting idea as well. Sugantan is the guy in the picture. He proposed an ensemble of epsilon values and an ensemble of external archives for a multi-objective particle swarm optimizer, a MOPSO. This is an acronym we came up with many years ago. So the idea is to avoid the pre-sampling to estimate epsilon. One of the reasons why epsilon dominance eventually was discarded as a good technique for solving multi-objective problems was that you had to run first the algorithm doing some pre-sampling of the population to estimate epsilon. Because without this estimate, it was very difficult to guess the value that you had to use. And this pre-sampling was, of course, costly because you had to evaluate the objective functions. So with this proposal, the idea is you don't do the pre-sampling. At the same time you are doing the optimization, the algorithm is estimating the value of epsilon. Okay, so I don't know if you have any questions so far. With this, we have finished the diversity topic. Yes.
Sir, by using hypervolume indicator, we can show the convergence.
Mm-hmm.
Right, sir? If the hypervolume indicator, value of hypervolume indicator is increasing by the iteration, right, sir? Then can we say the higher the hypervolume value of hypervolume indicator, the better the convergence speed?
It's not convergence speed, it's convergence.
If by the time speed is, by the time value of hypervolume indicator is increasing,
Mm-hmm.
and at some certain iteration, it remains the same after this particular iteration, that is the convergence of, we say,
Yeah, if you cannot increase anymore the hypervolume, that means you already converge to the true Pareto form.
that's right, sir, but it is increasing by the iteration.
Normally it does, yes.
So can we say, like, the higher the hypervolume indicator value, better is the convergence speed?
Yes, you can relate that, but this is tricky to do because for doing that, you need to know the hypervolume of the true Pareto optimal form. Only that way you can assess a speed of convergence. If you know the hypervolume of the true Pareto front, what you have to do is you have two different algorithms. So you run the two algorithms and you try to reach a certain percentage of the hypervolume of the true Pareto optimal front. For example, 98%. Whoever gets there first, that algorithm is faster. So one requires 300,000 evaluations, the only one requires 50,000. At the end, they reach the exact same hypervolume value. It's just one took more iterations than the other. So you can claim your algorithm is more efficient than the other.
But we need to have
The true Pareto optimal flow.
okay, sir. My next question is, when we are using some optimization algorithm to solve some specific problem, say I'm working in a networking problem, I'm using some optimization algorithm to solve a routing problem. So other than giving a mathematical modeling of the problem, giving the solution representation and derivation of the fitness function, what other novelty can we show, can we add to the paper, other than these?
That's all you need. That's all you need. It's just, it depends on the journal. It depends on the journal where you're going to publish. If it's a specialized journal, they will ask you reproducibility of the approach. So as many details as possible. If possible, the source code should be available. The source code program should be available so that other people can use it. Your data should be available. But this is only if you go for transactions on evolution computation, some journal like that. These things are important, reproducibility of your approach, that others can reproduce the exact same results you obtain. In other journals, if you go to an engineering journal, or in this case a networking journal, they probably won't care much. What they want to see is if your results are better than the results from others. That's really the main issue. Okay?
But the hypervolume doesn't increase monotonically with the number of generations. Sometimes it might happen for some generation the hypervolume is high, but in the next generation the hypervolume is less as compared to the previous generation.
No, it will never be less. Only if you screw up in the evolutionary algorithm. But
Sometimes I'm losing some solution.
yeah, but it won't decrease because the solutions, the only way for decreasing is if you move backwards. As long, it doesn't matter if you decrease solutions, as long as you are moving down, the hypervolume will at least stay the same, will never decrease. It could only decrease if you move backwards, if you went back.
But within, like, there might be small fluctuations.
Oh yeah, small fluctuations is possible, yeah, because of crossover or mutation, yeah. You can move one or two solutions, but the total hypervolume will be about the same, yeah.
So that is a point of debate, like how can you ensure the convergence and that? And for example, in a single objective problem, I can say for the last 10 generations, my solution didn't improve by a particular factor, like I would say 0.01. But hypervolume, there might be small fluctuations.
Sure, no, you cannot ensure. Through the use of hypervolume, you cannot ensure. It's just normally in practice, you stop when you don't see any improvement, let's say in 50 generations. You assume this is the best you will get. You don't know if this is the true Pareto optimal form. Probably it's not. But yeah, it's true. Actually, when we designed the micro GA2, we had that problem. That we were using not the hypervolume, but a direct comparison between iteration t plus 1 with iteration t. And what we found is there were, like the indicator will tell us you are still improving, but I was improving in the 5th, 6th decimal. So the improvement is really, nonsense. But for stopping the algorithm, the condition was no improvement. So we had to really be careful in designing a rule for stopping, because in a very small amount, because of the real numbers in the computer, that they are not real, they are really converted from binary, you may be biased in the selection. And the decision is not taken because you assume you are still improving. But that's not true. Because if you are using, for example, an 8-digit precision in your real numbers, and the improvement is in the 10th position, the 10th position contains garbage. It doesn't make any sense that the algorithm tells you are still better. Yeah, but better in a position that is beyond the accuracy I have. So this is a real problem, but this is not a problem of the hypervolume or any indicator. It's a problem of the precision in the computer. So you have to round up the numbers to decide. Otherwise, it will never converge. It will never stop. That's true. Yeah. Any other questions? I think I opened the wrong. I opened the same file. They all look the same. Okay. There are no more problems. We're going to move to test problems. This is a very interesting topic. You will see how crazy this thing has become in the last few years. Test problems is one of the things that people always want to know, right? Okay, you have all these beautiful, powerful, and magnificent multi-objective evolutionary algorithms, and the question is, what kind of problems can we solve with these magnificent algorithms? And in this area, something really interesting happened. In the old days, we didn't have test problems. We had a couple very simple problems, but over the years, people started to design test problems. Apparently, they were very challenging. Then we designed algorithms that could solve these challenging problems. And we started a race. People produced other test problems that were more challenging, and then we designed algorithms that could solve these test problems. stories started that saying, these guys are designing algorithms for test problems, not for general use, which is probably true. But, we were having fun. So today we have some really complex and nasty test problems, some benchmarks that are really complicated. Some of them are so complicated nobody uses them because, as I said before, it's not fun when nobody can solve it. If you can solve the test problems and nobody else can, it's a lot of fun. But if nobody can solve them, it's not fun at all. So you say, well, I haven't tried my algorithm. The truth is you have, but it didn't work. So these test problems have been there, and they have evolved in nasty ways. And sometimes people ask me, are these complicated test problems related in any way with the complexities of real-world problems? And the answer is, of course not, because we are computer scientists. We don't even know what the real world is. We don't care about the real world, right? We care about algorithms. So this for us was a game. We have test problems. They told us, if you solve this test problem, you will get a paper published in the transaction. Yeah, what the hell, we're going to do it. So we did it. Then they say, okay, we're going to make a more challenging test problem. But if you can solve this very challenging test problem, you can publish in the transaction. Okay, go again, do it. Then they bring a real-world test problem that we cannot solve. But we don't care much because, the guy who is concerned with the problem is somebody else. Right? This guy is not going to publish in the transactions anyway. So I say, yeah, okay. Let's see if we can do it. 98% of the time, we can solve those problems. We don't need, the powerful algorithms. We have algorithms in there that are under this glass that says, break me just in case of an emergency. These are too powerful. They are not for human use. So you cannot touch them because they are radioactive and all this. So this is like the nuclear bomb, the hydrogen bomb. You don't use these with, these trivial problems you guys give me. Those are reserved for the really, really difficult things. If we ever find a very difficult problem, we throw this one. For benchmark, for competitions, for all this, we use these algorithms because this is like the heavy weapons we have. The question is, does this make any sense? And of course, it makes sense to us, not to anybody else. The rest of the world, they think we are crazy, and we probably are crazy. We don't really care much about that. But this has become a really crazy race. Almost every year, some people try to design new test problems. They introduce more complexities because we don't want the game to be over. In the moment in which we cannot solve a particular kind of problem, then it will be over. Or if there are no more challenging problems, that will be even worse. Right? We have all these algorithms sitting there waiting for users, but they cannot solve these benchmarks. Some people have criticized this, for example, my good friend Hisao Ichibuchi, and he's absolutely right about his criticism, because we are not designing anymore algorithms for the masses. This is what we did in the 90s. Now we are designing algorithms for us. These algorithms are just, I will say, a byproduct of my ego. I want to show that I can outperform the other guys. That's all I care about. Of course, outperformance is also a very relative term because it's sometimes meaningless. We are outperforming the other algorithm in the third decimal. But that's good enough to get the paper accepted. That's okay. And sometimes we are very happy because that guy who has a very famous algorithm, his algorithm cannot solve this particular test problem, and we can do it.